right, so in this video, we're going to finish up the notes that I meant to do in class and have done, but we didn't quite get everything done you need to know to do this. So can you just make sure in your notes that you have up to, I believe, here. So what we did is we took a function, natural log of x. We built the Taylor series from scratch. It's centered at 1, so it's Taylor, not Maclaurin. We wrote the general term. Actually, I need to get rid of this. This is the general term here. So this is our a sub n. And we need to know if this right here converges. So we can try the ratio test to see if it converges. We've done ratio tests many times now. So a sub n plus 1 divided by a sub n, so multiplied by the reciprocal. And it's absolute value, so what I did is I just kind of ignore the sign changer here. And the reason that we got the answer we did is because, remember, n is our variable here. So it says n goes to infinity. I can use my horizontal asymptote here. Degrees are the same. So leading coefficient over leading coefficient, that equals 1. This is a constant. X is like a constant here, n is the variable. So I have x minus 1. So what this means is, like normally we end up with just a number here, not x. In order for the series to converge, my ratio needs to be less than 1. That's what the ratio test says. So I'm just going to set it less than 1. I put absolute value bars around it so that I can write this. And when I add 1 to get x alone, I've written it in the form of interval of convergence. Now right here, the interval of convergence is from 0 to 2. We're not sure about the endpoints. They might be included, which would be a bracket at each, or they might not be included, which would be parentheses at each. Either way, though, it's in between here. And you can think, okay, half of that is going to be the radius of convergence, so 1. Or you could always stop at this point right here. Whatever your absolute value statement is less than, that will be your radius of convergence. Now you might be thinking, oh, it's always going to be 1 because I said it less than 1. But that's not always the case, and I'll show you an example of that next. So what I'm going to do here is show you how to check the endpoints. And to check the endpoints, what you're going to do is do some more convergence testing. So remember, always do the ratio test to get the rough draft interval of convergence. Your job now is to decide, are there equal bars under here or are there no equal bars under here? So let me show you a visual of what's going on here for natural log at least. So we have natural log centered at 1, and we know it's between 0 and 2, maybe including the endpoints. So here's natural log of x. I did the general term here, and in order for it to really be ln of x, this goes to infinity. So let's watch what happens to my approximation, which is red, as my upper limit of integration or summation gets bigger. Now I have my endpoints here, 0 and 2. They're the blue vertical lines. So I'm going to hit play here. And notice as b gets larger and larger, in between 0 and 2, my polynomial approximation gets closer and closer to the black line, which is the actual function. And notice that it's only going to do a good job if I pause it right here at 20, from 2 maybe to the 0. So I need to check at 2, does it converge, and at 0, does it converge? Definitely in between it does. And if I let this go even higher, it will get even closer. So that's a visual of what's happening here. We're in an interval, and we want to know if it converges at the endpoints. So let's go back to the notes here, and this is how we're going to do it. So make a note of this in your notebook here. To check the endpoints, what we're going to do is plug the endpoints into the summation to create a series of numbers, and then see if this series converges. If the series converges, then the endpoint is included. If the series diverges, you don't include the endpoint. And when I say plug it into the summation, I mean plug it into this statement right here. So let's do each endpoint one by one. Let's start with the endpoint of 0. So what I'm going to do is plug 0 into my summation. So I'm going to add a summation bar or symbol in front of my general term. So write this in with me here. So what I did is I took my general a sub n here, and I added them all up. I put a summation bar. And right here, I'm checking when x is 0. So I'm plugging 0 in for x. That makes negative 1 right here. So now what I'm going to do is continue on my way here. That's the sum. If I have negative 1 to the n plus 1 times negative 1 to the n, same basis means you add your exponents. So n plus 1 plus n is 2n plus 1 over n. Now let's think about this. If I have negative 1 to the 2n plus 1, is this going to be a sign changer or not? If I plug 1 in for n, that'd be 2 times 1 plus 2. That'd be negative 1 to the third, which is negative 1. If I plug n equals 2 in, 2 times 2 is 4, plus 1 is 5. Negative 1 to the fifth is negative 1. And then if you plug 3 in, it'd be negative 1 to the seventh. As you can see, this is not a sign changer. Because if you take an n, multiply it by 2, that's an even number. But when you add 1, that's always going to be an odd number. And negative 1 to an odd number is always going to be negative 1. So let's go ahead and write it like that. It's always going to be negative 1. Now this right here is an alternating series. Actually, I'm sorry, it's not an alternating series. It is our harmonic series. Now some of you, when I say harmonic series, you kind of look at me with a look like, what the heck is a harmonic series? Remember, the harmonic series is a version of the p series. It's the p series when p is equal to 1. And we know the harmonic series always diverges. So if you have a constant, you can actually pull it out of the summation, just like we could with an integral. So now I have that. So I just have a divergent series, but with all negative values, so it's still going to diverge. So because it diverges, that means x equals 0 is not in the interval. And I meant to label this as harmonic. So you don't want to forget what harmonic is. Okay, so x equals 0 is not included. So that means right here I'm not putting an equal bar under it. It's everything up to 0. And that makes sense because if you look at the graph of it, there's a vertical asymptote right here. So it makes sense that doesn't converge there. Okay, back to here. Now let's check x equals 2. So do this one with me here now. I'm going to do the sum, n equals 1 to infinity, negative 1 to the n plus 1. This time, instead of plugging in 0, I'm going to plug 2 in for x. 2 minus 1 is 1, all over n. So now I have the sum, negative 1 to the n plus 1. Well, 1 to anything is just 1. So now I have this. Okay, this is a sign changer. Because if I plug 1 in, 1 plus 1 is 2. Negative 1 to the second power is 1. If I go to 2, plug 2 in, that'd be negative 1 to the third, which is negative 1. So this is an alternating series. And it's almost the same as harmonic. It's the alternating harmonic series. So I actually want you to make a note of this here because we're going to use this phrase in class. And it's just something you should know as a calculus BC student at least. Alternating harmonic series. And if you do the alternating series test, you can see that the limit... Oh my god, hold on, my dog's going crazy. Alright, so anyway, alternating harmonic series. If I do the alternating convergence test here, the limit as n goes to infinity of the absolute value of the terms goes to 0. It's alternating, it's decreasing. Therefore, I can say it converges by the alternating series test. So therefore, my final interval of convergence, my rough draft was this. My final version is this. I'm going to put an equal bar here because at 2, it converges. So I include it. This can also be called the domain of the series. I remember the radius of convergence was 1. Okay, so let me do one more just to make sure that in class will be all good to go. So for this one, I'm going to get a new example. Here's what we'll be doing. So what I'm going to do is we want the interval and radius convergence again. So remember, you always do the ratio test, and then you check the endpoints. So let's do the ratio test. So that means I'm going to do this. So let's do the limit as n goes to infinity. Ratio test. So that's always the first thing you do. Then you get your rough draft, and then you can check your endpoints and get your final draft. So I'm going to do a sub n plus 1. And dividing by a sub n is the same as multiplying by the reciprocal. So I'm just going to go ahead and save myself a step here and do that. What I'm going to do is start to simplify this a little bit. So in the numerator, I broke up and gave each exponent a base of x and multiplied. Right here, this is n squared plus 2n plus 1. And then when I add another one, it becomes n squared plus 2n plus 2 times n squared. Sorry, this was supposed to be an x to the n here. So anyway, I'm going to start to clean this up. X to the n cancels. That's gone. Now I'm going to write it like this. And remember, n is the variable that's changing here. So as n goes to infinity, degrees are the same. Leading coefficient over leading coefficient is the horizontal asymptote, which is 1. So all I'm left with is 1 times x, which is x. So that's my ratio. In order for it to converge, I need to set the absolute value of it less than 1, which gives me my rough draft integral of convergence of this. That means right here, this is my radius of convergence. So radius of convergence. So if you need a little visual here, I'm going from -1 to 1. Possibly the endpoints, it could be parentheses or square brackets, we're not sure. Half of it, though, is the radius. So half of the distance of 2 is 1, which makes sense because you set it less than 1 right there. So I'm going to check my endpoints one by one. So I'm going to start with my endpoint of -1. So when x is -1, I'm going to plug it right into here. And we'll see that is going to give me just a series of numbers. And you're going to use your convergence knowledge to see does it converge or diverge. So instead of x to the n, let's do -1 to the n over n squared plus 1. This is definitely an alternating series because this is the sign changer. So the limit as n goes to infinity of 1 over n squared plus 1 is 1 over infinity, which is 0. It's decreasing and it's alternating. So I can say that this converges and by the alternating series test. So therefore, I'm going to go back here and edit my rough draft and whoop, put an equal bar there. Now, let's test the endpoint of x equals 1. So let's take our summation and let's plug 1 in. So that'd be 1 to the n. I'm plugging in right here over n squared plus 1. Well, 1 to the anything is just 1. Now, this looks a lot like a p-series 1 over n squared. Let's see if we can do direct comparison, like if the direction of the inequality is the right way. So let's compare to 1 over n squared, which converges. And it's a p-series because p is 2, which is greater than 1. So let's compare 1 over n squared plus 1 and 1 over n squared. So if I divide by more, it's going to be less. And this is good because this converges. It's an upper limit, or an upper bound, I should say. And this is less than something that converges. So this definitely converges, which is good. I don't have to go to limit comparison. So I can edit again my rough draft here. And this is my final interval of convergence. It converges at both endpoints and everywhere in between. Okay, so these are the notes you're going to need. I'm going to give you a couple problems to try for class. Email them to me Wednesday night by 9 p.m. All right, so here are your 3 problems I want you to do. Find the radius and interval of convergence. Make sure you show your work. Make sure you clearly do your endpoints. And again, email notes and problems to me by Wednesday at 9. See you later.